This is the two-disc problem. People find this one quite confusing to think about. So we've got two discs. We'll give them equal I. Now this is the only one that's rotating at the start, and it's rotating clockwise. So we'll give that one an angular momentum of L equals I omega I for initial omega. Now what we're saying happens is they're actually close together when this whole thing's happening, but that one's not rotating. Then that one is moving just very slightly and touches that one and exerts a force on that one, and so this one starts to rotate in the opposite direction, because this angular momentum up here was a clockwise angular momentum. And what I'm saying is that's the total angular momentum for the system, I omega I, and if the contact is long enough for this one's angular momentum to equal this one's angular momentum but in an opposite direction, then we know that this one will now have, afterwards, they will both have an angular momentum which will be equal to omega I over 2, but this one will be in anti-clockwise direction and this one will be in clockwise, and so their angular momentums will cancel out. And so after that little touching, my question was, how can they now have zero angular momentum for the system when we started off with this much angular momentum at the start? And that's what I proposed to you. Now my solution to this was this. I said what actually happened was, and I've said this a few times, was not to forget that when that contact happens, a force is exerted, and the force exerted on this one here, we'll call that force, causes that one to rotate, because that force is not exerted through the center of mass. Therefore that one will have a torque exerted, it will rotate. There's an equal and opposite force on that one. That one will slow down. If the force is with sufficient time, we'll get the omega I over 2 for both of them. But let's not forget the fact that that causes this one to have a linear acceleration, and this causes this one to have a linear acceleration. So if we take this as our reference point, we can see we're back to having a clockwise angular momentum, and hopefully it's going to equal what we started with. And therefore in our little system, isolated system, we've got no loss of angular momentum. Angular momentum is conserved. So does that work? Let's actually do the maths for it, because we like that sort of punishment. Let's write down a few things for a start. The angular momentum they both end up with, these little disk guys have a rotational inertia of mr squared over 2, and we're saying that afterwards, so that the omega I is going to be also over 2, because it's cut down in half. Alright, so what we want to do is have a little think about the acceleration. So if it goes from omega I to omega I over 2, and then the actual change is, or the acceleration, delta omega over delta t, must be equal to omega I over 2, t equals alpha. Right? So that's the angular acceleration that must be exerted on these little disks. Now how's that going to help us? Well, let's go back to the fact that there must be a force exerted on these disks when that happens. So that force times the radius, alright, must be equal to I alpha, but I is equal to mr squared over 2 times alpha, alright? But we just said the alpha was equal to omega I over 2t. Okay, so looking at that so far, let's just smooth things out a little bit, and we've got the force must be equal to mr, because the r is cancelled, omega I all over 40. Right? So looking good so far. We've got what should be the force acting on each disk. Remember, this is just on one disk. So what's alpha, or what's acceleration going to be equal to? Acceleration equals force over mass. Alright, so we've already got an expression for our force. So we end up with the mass cancelling out, so we just have r omega I all over 4t, right? That's acceleration. Now, so that's the linear acceleration. Now, assuming that's constant, velocity equals linear acceleration times time. So that's our acceleration. So we multiply it by time, and we've got our velocity equals r omega I over 4. So we've got the velocity that they're going at. So now we can figure out the angular momentum for one. Now, angular momentum equals mv delta r, or perpendicular distance to r. So that's going to be equal to m r omega I all over 4 times r, which equals m r squared omega I over 4. Now that was for one disk, so we can double that for 2 disks. So that's for one disk. So for 2 disks, it's going to be equal to m big R squared omega I all over 2. That's for 2 disks. Now if we go back to our original angular momentum for the system, it was equal to I omega I. So that's m r squared over 2 times omega I, which is the same. So it looks like my theory works.